Hey everyone, today we will talk about PostgreSQL uh, observability. My name is Peter Zaitsev, and I am speaking here as a co-founder at Skarut, which is an open source observability solution. And also many of you know me as a founder at Percona, the company which has been working in a database space for almost 20 years. So we have a lot of insights in that area as well. So let me start by talking about how modern systems look and how they are different compared to what you could see 20 years ago when I was starting with my first database development. At that point, many systems, at least those who would be in internet, would be kind of small and simple. You would have application server, database server, right? Maybe a couple of application servers, right? And what that means is we didn't quite really need a lot of a complicated observability tools. You could really open a shell in all of your systems, right? And I remember if something goes wrong, I could literally just, in a few clicks, check all the logs out there or load on the service and find out what went wrong. The modern systems, though, are much, much more complicated, especially those which use microservices or related concepts. We often have multiple of those services talking to each other. And in many complicated environments, we have really hundreds of thousands of those systems. And also what is interesting, even things which have been sort of like a simple, not a service in the past, now are complicated and often not very transparent services. Think about storage. In the past, storage would mean a simple local disk or maybe RAID storage, very simple to understand and troubleshoot. And now if you're using EBS, that is ginormous and complicated system on its own. Another thing for information, interesting thing about the modern systems and modern teams is what often you have a siloed knowledge, siloed responsibility, and siloed monitoring systems, right? What that means is there would be some network people which have one system, and then would be database people which have another systems to understand what's going on. And then there's going to be, let's say, storage people, right? And what that means is it's kind of hard to find the problem in those complicated environments. Right. So what that also means is what often it's harder to find what is that specific component which has a problem, right, and for you to dig deeper into compared to really finding specific cause of a problem. Now let's talk a bit about what observability is. Now, the simple way to talk about the observability is that is ability to answer various questions about your system. And of course, we are talking about observability in this case as it relates to the system's performance and availability, right? So what that means is we need to understand how system is performing right now, how that performance compares to previous uh, time. Maybe you have some requests are failing, why that is happening, or maybe they're taking longer than expected. If you think about observability, right, it is really the most useful when the system does not functions as normally, right? Like we have a failure scenario and we need to fix that. Well, if a system works perfectly well, no problem, no slowdowns, no cost overruns, then often we don't really think we need the observability. Now, if you talk about our old application setup, right, as I mentioned, what is going to can potentially go wrong here? Well, we can have problems on the application side, the database side. Also, you can see those related to the network connectivity issues or delays between those two, as well as a few more. Now, what I think is very interesting here is what you will find a lot of observability tools which will be very like database focused, right? We can look at the database as a an only database. You would find what not everything exists out there. Some of those are really limitations of how a PostgreSQL information capture is designed. Like, for example, error counters are not included in a PG statistics, right? You will see per query, per client query statistics are not stored out there, which can be very important, right? For example, if one of your application instances is malfunctioning by creating a lot more database loads, for example, because of caching failure or something like that. And also, what is very important is we have a network which is not included in a latency, or if a network is not working, right, and so their application is unable to connect to a database, well, the database will be just think, hey, I'm doing fine, and just nobody asking me anything. We like the concept here in observability, which can be defined as the customer is always right. And what that means is what the failure or the latency have to be thought about as from the position of a client or a customer, right? And that means there's several levels metrics, such as availability, latency, distribution of said latency, should be measured on the client and the client side. And then the database side metrics, they're also very, very helpful, but they're helpful for deeper troubleshooting to answer questions. Why? Why is a query slow, right? Why is connection being refused, right? Or something like that, right? And one example you can think about here, right? If you look at from your normal right? If you are at your home and there is no power, there is a power outage, right? You probably don't want to tell utility company, hey, you know what? We looked at our power plant and it's actually working. Well, you know what? A lot of other things could go wrong. And what I know as a customer, I don't have a electricity warrant. So go and fix that, make it work. Let's go deeper and see what we can want to know. If you think about the client size, we are looking at the queries from a given app instance to a particular database instance. And here we can look at errors, and both on the TCP level, right? Like, for example, oh, a connection is refused, right? Or I can't reach the host and so on and so forth, as well as the L7 protocol level. And this is kind of the fancy word to describe on a PostgreSQL protocol level. How can we get those statistics if you think about the big picture? Well, one way, if you look at the modern observability, is to use OpenTelemetry. OpenTelemetry as the case, they are awesome, right, if you can get them. And another way is you can also use eBPF to capture queries made. Of course, there are some other custom solutions, but if you think about what is the most commonly used in practice, it is probably between those two. If you think about the OpenTelemetry, it is awesome, right? It can really get the data about all the services, not just about Postgres, right? It's very commonly used in the microservices in microservices environment, and specifically capturing a lot of data from HTTP. Right, but the challenge with that is, of course, it's requires additional implementation, and also in some cases it can see as an additional performance overhead. Though we can see things like that. Hey, in a grand scheme of our request from a user which came through multiple services, we can see one of those requests are access to a database, which shows us stats like that, the query, the latency that was successful, and so on and so forth. Now, the challenges with OpenTelemetry and really that whole distributed trading approach are those. It's huge volumes of data, right, you have to deal with. So a lot of folks have to sample the data, right, or only in the have it used for some services. And that is especially becomes important because if you look at a lot of SaaS, cloud-based observability solutions like Datadog, they make the storage of the telemetry data very, very expensive, right? I've seen some people spending almost as much on their observability as on running their environment. It's also hard to achieve 100% coverage because you may have a legacy services you don't want to modify. You have some proprietary services as a part of your stack, which you cannot plug OpenTelemetry into, right? So that can be complicated, and that is the downside. The other approach, right, and by the way, Kahoot uses both approaches. It allows you to either provide you or your OpenTelemetry data, right, as well as does with eBPF instrumentation. With eBPF approach is we can sort of get a lot of those data after magically, right? We have an agent which can just capture a network call for each progress of a node, and we can see if those connections go to Postgres by analyzing the protocol, right? And the wonderful thing here is doesn't require code change. It can really implement any services, including third-party services, can be integrated in minutes and so on and so forth. Now, often people who are familiar with a lot of kind of old age network, sort of like a sniffing, can say, well, but you know what? There is a such thing as a SSL TLS, network encryption. And you know what? That means all we get is garbage, right? The thing is, with the eBPF, we can actually also intersect the calls before the data is encrypted, and combining that data with network traffic actually understand specific query. Now there are a number of open source implementations which support Postgres. Kahoot is not the only one which you can check out, but we will focus on Kahoot here. So how does eBPF instrumentation works? Well, what we can do here is when we can see when any application has a connect call, we can see from what P that originates, as well as to what destination IP and port. With that, we can build the map between how all those applications connected and what the application is queries, right? Hey, here it's queries Postgres, here is its OpenAI API, here is something else, and then we can intercept various calls, so we can monitor for PostgreSQL protocol frames. Then what happens is in the kernel space, and that is something which you want to take very small, very tight, we can really parse only about 10 bytes of payload to figure out, oh, that looks like a PostgreSQL protocol. Then we can capture the payload, which is up to 1 kilobyte, which goes transferred to the user space, along with additional information. And then we can, on the client app, which is in this case is a Kahoot agent, we can reconstruct information about what client that corresponds to, what database it corresponds to, and so on and so forth, right? Additionally, there is some magic which Kahoot agent is doing, such as working with prepared statements, right? So it is able to map statement ID to the statement text, so we understand what queries are really being running. Now, eBPF is awesome, and that is a relatively new technology, which was really designed with all the learnings from the industry about how to get things safe and performant. Right? Why I think the eBPF being so successful in the kernel space, in particular, because in the past a lot of observability depended on some sort of custom kernel models. And if you have some custom kernel models with a custom bugs, which causes a kernel crash, that is not good. Right? You don't want to crash a kernel to get more observability, right? The eBPF program, though, it runs inside the virtual machine inside the kernel. And additionally, to load that in that virtual machine, it passes through a bunch of checks. right? So that verifier, it kind of checks all the executions path within that little code which you upload to make sure it cannot loop, right? It has a finite complexity, right? And so it is a very, very safe to connect even to your some very important calls. And then also it is done sort of asynchronous. There is a limited buffer space in the kernel where all events are stored, and then their client running the user space need to consume that. If a kernel produces events too quickly, you may lose some of events, but you are not going to just block and say, oh, like, well, I am not looking for this thing to happen just because there is not I'm not able to process my observability events very quickly. So that means the EVF-based applications are typically very safe to run in your database. Let's see what kind of queries we can get in this case from EVF metrics and in Kahoot in particular. First, we can see here the application which talks to the free database instances, right? And we can see both requests per second as well as the latencies. In this case, we're showing average latencies, but you can drill in to get a Postgres, or you can get a distribution as well. What you also can see is actually using all that kind of information about kind of how communication happens. Kahoot is able to identify the PostgreSQL cluster, which has one primary and two replicas, as well as some backup job running and so on and so forth, and they kind of consolidate that in the same thing. And you can also see there are some connections happen within that cluster, as well as something which is hitting the K3S right now, right? In this case, we don't have any errors, but if would be any errors on connection or on the latency, we would see that as well. Now, if you look at eBPF-based traces, we can see something like that, right? We can see in this case the distribution of the latency, which I think is awesome, in particular in database queries, right? Which can range from from fraction of a milliseconds in how long they take to execute to many minutes, right? And in the worst cases, even hours. All right, so the latency really help us to understand what's going on. And if you start to get outliers, you can really see that. And we can see we can have a specific specific queries as well, which here is captured from EVF. Now, EVF metrics and traces, they give us high-level information, right? They can tell us, hey, this is what's going on. The queries became slow, or there are more errors. But why? That is not enough. And this is where we need to collect some other metrics, which we do. So here are some of the ideas why your queries can be executed slower than usual. And again, this is kind of not really exclusive, right? But this is something which is one of the typical cases, and especially which comes from environment, right? Because if you look at when things get slow with a database, you can see things kind of put into things. Like one is very sort of like a environment and resource based, and then there is another one which is like a very database specific things, like oh, my database decided to execute this query with a different plan, or well, you know what, like there is no index. Maybe there was no index at all, or maybe somebody drop the index and it's not being picked, right, because of some cardinality estimates, whatever. So let's look at those typical examples. If you think about the CPU, one I think which is like a very awesome metric, and it's often undervalued, is not just CPU usage, but also their CPU delay. What does that mean? Well, the CPU usage is, showing you, hey, the CPU is, pegged at 100%, right? And obviously, if you think about the process, and you cannot, when you're given a process is placed on the CPU, right, it cannot run faster than the performance capabilities of that CPU. But what often happens in Linux, especially when the system is overloaded, is what the process is not placed on the CPU. It's waiting in the queue because there are too many processes which needs to run. And we can measure that, right? And that is, I think, one of the very, very good metrics to look at that, because if you are having a lot of CPU delays, then you are surely having the latency which could be overall much better than you are currently having. The other thing which exists, especially in a Kubernetes and all containerized environments, is CPU throttling. What happens in this case is what we may have some quotas supplied for a given container, and then if their CPU gets if the container gets throttled, right, that is also another weight which is unnecessary. That means you often want to configure the CPU allocation in this case, so you don't have any CPU throttling, right, or very limited. And then, of course, we can look at the standard node metrics, right, where we can think about the total CPU usage as well as what specific consumers are using that CPU, and if CPU is overwhelmed, right, then you can look at whether that's database related, or it may be related to the other processes which are still in the process, right? So for example, sometimes you can have a backup process which runs on the same host as a database, which consumes too much CPU, right? Or sometimes people have some ETL or other process in which needs to run the same location as a database, which can consume a lot of the CPU and memory and cause the database performance issues. Now, what we can also do in this case of wonder is, if I'm bottlenecked by the CPU, wouldn't it be wonderful for us to be able to look at how much CPU different queries take? Now, in a Postgres, as of right now, there is no exact information about that, but often we can roughly the query execution time, especially if you subscribe from that IO time and so on and so forth, right? And that is where we are able to capture that information and give you some ideas what queries may be responsible for that. With that, I think it's is good to talk about the visibility, right, and how to get that information. Now, it looks like very simple, right, to say, hey, guys, well, we are, can just take a look on a pgstat statements, right, and it's everything, it's quite trivial. Well, it is not quite so. Now, if you look at the pgstart statement, the classical tool, right, which gives us a lot of information about the queries, first, it only shows finished queries. So if I have an instance, right, which, for example, got some very bad queries, and I have, 10 queries in parallel, which has been running for 3 hours each, I would not see that in a pgstat statement because queries haven't completed yet, right? And also, as I already mentioned, it does not include the failed query, right? And the failed query actually could fail, but only after it used a bunch of CPU resources. So that is another thing to consider. Another data source we can look at is a pgstat activity. which shows about the queries which are happening now, right? And what Karoot is able to do in this case is actually combines the information from pgstat statements and pgstat activity to really give you that very good information about what queries are consuming the CPU, wherever those queries are currently running or have been completed. And I think that is a very very cool in this case. So how can you play with that? Well, now here is exactly this simple way to look and correlate things. We can take a look at the queries on this instance, and we can see, hey, this is intentionally bad query causes a spike, and we can also see what that has caused 4x CPU increase, right? So you can, if you are seeing, hey, there is a CPU increase on your system, right? You can go to the queries and instantly see what is causes the problem, right? Now, the other thing, which I think is a very important thing to take a look at, is IO-related metrics. If you look at the IO related issues, is what you often would look at the latency, right? And if you look at the latency, it should be pretty stable if system is not overloaded, right? If you look at this case, how a storage typically behaves, if you are putting it at the load, it can handle it, doesn't have to queue. You will have like a rather predictable latency. If you are putting too much of a load on it, right, then the storage system will have to start queuing those requests because it cannot process all of them in a parallel, and that is where the latency would start to increase, right? And we show that information not only as latency, but also the information as number of seconds wait on disk spending on the IO, right, with the IO utilization stuff. The other thing which you often want to consider in this case is number of reads and writes. Wherever you have as your storage, is that a local storage? Is that some sort of cloud devices? There are limits in terms of how many max IOPS per second you can get, and I think that is a very helpful to understand where your IOPS, what you currently have, are compared to the device capacity. Unfortunately, in the modern environments, we cannot get that capacity from IO device. We cannot tell, hey, you know what, this device only can do up to X amount of IOPS, right? And if you're doing this close IOPS, then you may be pushing close to its limit, right? As we can get with a CPU, but it's still very helpful. And the same goes with bandwidth. The bandwidth, there are, again, of limits in terms of what your device can provide, being that your local devices or cloud devices, and that's is very good to know those limits, because in number of cases you may be pushing on them, which limits your database performance. So with all of those metrics, so what can you actually get in terms of explaining the IO anomaly? Often when you have an IO overload, which is caused by a very IO intensive query, you will see something like that in your IO, right? You will see what there is a spike in IO latency, IO utilization, probably IOPS, and bandwidth, right? In many cases, they're kind of all correlated to each other, like, but sometimes not so much, right? For example, we have a massive, massive table scan, a lot of sequential reads. You may not have a huge spike in IOPS, but you may have a huge spike in bandwidth, right, and stuff like it. And then again, you can go to the query and information and probably see the queries which can relate to your IO anomaly. Okay, now I have explained how you can do that. And you say, well, guys, that is awesome. That is a tool, right? But that's too much looking, too much thinking. And in this day and age, cannot AI do that for you? Right, and that is actually something what we have been working a lot with Kahoot recently to let it to really identify the root cause by using a lot of information we have about the system structure as well as the modern LLMs, and it's actually shows to be pretty cool, right? I wouldn't say it can solve all the cases, but large amount of cases. And what I wanted to show in this particular example, it's not only able to look specifically inside the Postgres and say, hey, this query looks bad, but it also can find out more complicated dependencies, right? Like in this case, we can see the application was deployed, which caused the latency spike, right? And it can see, oh, the database is overloaded. From that, we can see who is sending those requests, what that correlates to, right? And suggest what that is probably comes from this deployment. And as such, fixing database performance is not about fixing a database, but that is fixing something in the application, right? And I'm sure a lot of us database experts have seen that exact scenario more than once. So let me finish up with this. Like, how do you want to be in the best position to really help your business to resolve the issues? One is you want to ensure there is observability is complete with no blind spots. You also want to ensure you have a tools helping to identify your components to experience the issue, right? So then you can understand who is responsible for them, and then use skill appropriate tools to solve them. Sometimes under crunch, less is more, and 1,000 metrics and hundreds of dashboards may be too complicated. And finally, what you can see from observability tools is make sure we provide you the evidence you can use for escalation to another team or vendor, which I think is a very important those days when we often have a shared responsibility for our systems with, cloud vendor, managed services provider, and so on and so forth. With that, that's all I had to say, and thank you.